This is ECE 343, Signals and Systems, Chapter 3, Part 1. Chapter 3 is the time domain analysis of discrete time systems. In order for us to do that, we do need to wrap up a few details about discrete time signals. We'd like to look at a couple classifications of discrete time signals, look at operations on discrete time signals, and then look at a couple discrete time signal models. Many of these are going to look very familiar from what we saw in continuous time, but there are some notable differences that really need to be highlighted, so I'd like to take a few minutes and do that. We can recall from chapter 1 that a discrete time signal x of n is a signal, right, that is defined for the independent variable n, which we take to be as time, and that time variable n must be defined for the integer set. So a discrete time signal is only defined on the integer set n. Like all signals, we can find a variety of classifications for those signals. We'll start out by reminding ourselves of a classification we use for continuous time, and that's between energy and power. And energy and power classification for discrete time signals looks very similar. If you take a look at the equation for energy for a discrete time signal, we just say the energy of signal x is equal to the summation on the independent variable n going from minus infinity to infinity of that signal's magnitude squared. This looks identical to what we saw for continuous time, except the integral of continuous time became a summation in discrete time. Of course, that's pretty obvious because a discrete time signal doesn't have that continuum by which we can do integration. The analogous operation to integration for discrete time would be summation. Power is very similar. For power, we are looking at a normalized energy, so we're going to sum up the magnitude of x of n squared over all time, and then we're just going to divide by the number of points. So we'll divide by 1 over 2 cap n plus 1, and the limit as n goes out to infinity. You might wonder why that plus 1 is in the denominator there. That plus 1 is just because 0 is a placeholder. One of the things that we're going to find with discrete time signals is that individual points matter in ways that they just didn't for continuous time. In continuous time signals, you had an uncountably infinite number of points, and in many cases, individual points are lost in that uncountably infinite number to where they don't individually matter. That's not the case in discrete time. In discrete time, every single point matters. Every single point is one of a countably infinite number, and the fact that they all can be counted, that they each have their own kind of individual identity, makes them have a weight in a way that maybe we didn't see in continuous time. You probably could be a little sloppy in continuous time, for example, in whether you included a boundary or not, whether you said t less than or equal or maybe less than. In discrete time, it's going to make a big difference. Doing something like n less than or equal to 0 versus n less than 0 definitely will cause noticeable differences. So it's something we have to be particularly attentive to, this idea that in discrete time, individual points matter. We do say a signal x of n is an energy signal if its energy is a finite number, just like continuous time. And we would say a signal xn is a power signal if its power is finite. Much like the continuous time case, energy and power are mutually exclusive conditions. So if you are an energy signal, you know the power is 0. And conversely, if you know you're a power signal, well, then the energy is infinity. There is a special case, just like in continuous time, where we can simplify the power equation. So if x of n is a periodic signal with some period cap n, and just remember, because it's a discrete time signal, that period must be an integer, well, then we can compute the power, right, just by looking at those n points that form that period, right? N equals 0 to n minus 1 of that signal magnitude squared divided by the number of points, so 1 over n. You could, of course, choose any n consecutive points. It doesn't have to go 0 to n minus 1. You could go 1 to n, or you could go, any other set of points that are all connected together that are n in length. The next section that we're going to talk about are operations on the independent variable. We've done a lot of these for the continuous time case. And I think you will recognize, or at least see a lot of similarity in notation here for discrete time when you compare it back to that continuous time case. What I would like to do is I'd like to go ahead and state these different operations. We'll get them down on paper. We'll look at a couple signal models, and then we'll do some examples just to make sure that we can utilize these different operations correctly. So much like continuous time, if I just put a minus sign in front of the independent variable, such as what's shown here, x of minus n, that's just indicative of reflection. So we can reflect a signal about the vertical axis, right? Just by negating the independent variable. If I take n and replace it with n minus some cap n, of course cap n has to be an integer because discrete time signals are only defined on integers. This is a shift by that integer amount n. We can remember some rules, just like in the continuous time case. If cap n is greater than 0, it's a shift right. If cap n is less than 0, it's a shift left. Of course, if you don't want to memorize those rules, we can go back to our understanding of functions being consistent mappings. And you can just plug those into that mapping, that new argument, and not have to memorize all those. We'll show that by example. The next case is x of cap n times little n. So we are doing some form of scaling of the independent variable. We talked about time scaling in continuous time. Here, n is an integer. You might have something like 2, so x of 2n, for example. If you think back to the time of continuous time, when we had something like x of 2t, that was a compression operation. Here, we're going to call that compression-like operation something different. We're going to call it downsampling. Now, downsampling, while it is similar to the continuous time compression operation, discrete time's downsample operation is fundamentally different. It is going to cause a loss of data. How do we carry it out? Downsampling by an integer n, essentially, right? Just says that we're going to cut out n minus 1 points out of every n points of our original signal. So if you had a signal that was 20 points in length, 20 non-zero points, for example, and we downsampled by 2, the result would only be 10 points that were non-zero, right? We're going to throw half of them away. A downsample by 3, we're going to throw away 2 out of 3 sample points, and so forth. So the larger the n, the more data is lost. And once that data is lost, you can never get it back again. Compression for continuous time, you just squeezed everything together, and you could get away with that because you had an uncountably infinite number of time points. You could just keep squeezing, and those points always fit. In discrete time, you only have the integer set that you can work on, and when you squeeze things down, when you squeeze them in a compressive kind of way, there's nowhere to put those data points, and so they pop out and are eliminated from the signal. They're lost, and once that loss occurs, you can never get them back. The converse to this idea of a compression operation is something more akin to expansion. So we can take a look at a signal x of n divided by cap n. Notation here isn't exactly perfect, but I think it gets the basic idea. This is called the upsample by integer n operation. And the rule is we've got to figure out some way to stretch this signal out, right? So that it's n times as long as it was before. Because it's a discrete time signal, when we try to stretch, we don't know where to get those new points. There are no new points to get. You start stretching things out 2 times, 3 times longer, you need to put new data points between what was your previous data points. And because it's discrete time, we don't have any indication of what that data should be. So one rule for this, it's not the only rule, but it's a very common rule. One rule is to just fill all those gaps that are formed by stretching out your waveform, right? We're just going to fill those gaps with zeros. So an upsample by integer n is a rule that just inserts n minus 1 zeros between every sample. Unlike downsampling, data is not lost in this. We're making up some data. We're making up a bunch of zeros. That might or not be like something that looks like you would expect with a signal, but at least we're not losing data. So if you were going to look at these two operations, downsampling or upsampling, and you were going to wonder which one might be more dangerous, downsampling would be more dangerous. Downsampling can cause the loss of data. Upsampling, you don't lose data, right? You're inserting data that might or might not be perfectly reflective of the underlying trends of the signal, but at least you don't lose it. This is somewhat similar to the continuous time expansion operation, but unlike continuous time expansion, upsampling fills unknown spots with zeros, right? We just can't just stretch this continuum of points. We have to find some new points. We don't know what they are, so we just guess zeros. Some basic functions, and again, these will look very familiar to you. There is a delta function as a function of the discrete variable n, delta n. That's defined as 1 when n equals 0, 0 otherwise. You can't do this with a Dirac delta function. Remember the properties of a Dirac delta function. It said that it was 0 everywhere except for when the argument is 0. Well, that's certainly true in this case. So that's a shared property between this discrete time delta and the continuous time Dirac delta. A continuous time Dirac delta, though, called for what else? It said that the integral of the delta function had to be 1. Integration is not a defined operation in discrete time, so we have to come up with something similar. And we'll just say that the sum of delta function across all n is 1. So take those two together. It has to be 0 everywhere but 0, and it has to sum to 1 rather than integrate to 1. And then we know that it's going to just have a value 1 at n equaling 0. This guy is called a Kronecker delta function, and it's a little different than the Dirac delta function in that it's completely realizable. Remember that the Dirac delta function, right, had to fly off to infinity at 0, at least for the continuous time, right, because it was infinitesimally narrow, and you had to make it integrate, right, had an area of 1, and the only way it could do that was by having infinite amplitude, if you will, at that single point. For discrete time, I can get a sum of 1 just by having a nice value 1. So Kronecker delta function in some ways are just a lot nicer than the Dirac delta function because they are completely practical. They can be realized on real systems. Just like we had a unit step function for continuous time, there's a unit step for discrete time defined in a very similar way. So u of n is 1 for n greater than or equal to 0, and it's 0 for n less than 0. A reminder though, right, since this is a discrete time function, it's defined on discrete values, right, of the independent variable. And really, we are not saying anything about what might happen in between those samples. So we'll see this come back when we do some examples. All right, so let's go ahead and take a little bit of time and work on some examples. We'll slow it down a little bit. I'm going to start out with a signal x of n, and right now I'm showing the signal x of n is defined as n times the difference u of n minus u of n minus 5. We'd like to do some basic operations on this guy. So I'd like to go ahead and do things like reflection and shifting, both left and right. I'd like to be able to downsample and upsample and think about these various operations. In order for me to do any of these guys, I definitely want to be able to get an idea, a visual of what this signal looks like. So let's go ahead and plot this guy. This is also good for the example that the plot of x of n might surprise you just a little bit on first blush. It might look a little different than what you would have expected for continuous time. So let's, as a very quick aside, think of what a continuous time similar signal, what we might have guessed a similar looking continuous time signal was. We might say something like an x of t, right, equals t, and we could do a u of t, right, minus u of t minus 5, something like that. And if I was going to plot that guy out, right, I would come out here 1, 2, 3, 4, 5. So the u of t part, right, that u of t tells me to start at 0, and the u of t minus 5 tells me to end at 5, something along those lines. And it's going to be parameterized by t on that. So I should get this ramp function, something like this. So when I think of this continuous time version of t times u of t minus u of t minus 5, I get this nice ramp looking function. It starts out, right, at 0 and it ends at 5, something along those lines. Let's see how this translates for the discrete time case. I'm going to start in a really methodical way. It's going to seem maybe just a little bit weird that I do it out this way first, but I think it will become clear why I'm doing that here in a second. So I'm going to draw a couple axes because I would like to look at this first portion of the signal, right? That stuff inside the parentheses, u of n minus u of n minus 5. So the top axis here I'm going to use to plot u of n, and then the bottom axis I'm going to use to plot u of n minus 5. So let's go ahead and do u of n first. We know, because we just defined it, the unit step function is one that is 1 for n greater than or equal to 0, and it's 0 for n less than 0. So I have u of n here. We just use it direct by definition for n being 0, 1, 2, 3, 4, 5, 6, and forever on. We're going to go ahead and have that guy have a value of 1, and I'm going to put a value of 0 for all those integer values to the left. I might label a few things in here. So I had n equals 0, 1, 2, 3, 4. I'm going to go ahead and put 5 in there. Going to label this guy n. I'll put my u of n over there as well. I would like to ask that when you're drawing out discrete time signals, that you use a kind of a notation, something like this, right? That you go ahead and you draw those stems in there with a little dot at the top at the height of the signal, right? And that you include things like when it's 0, go ahead and draw that dot at 0, just so that I know that you know that it's 0 at a particular place. Okay, so how do I get this u of n minus 5? Let's go through the math on this, even though you probably could guess it. The second operation on the independent variable that we just introduced was this idea of a shift operation. We said u of n minus some cap n was a shift by cap n. If cap n was greater than 0, it was a shift right. If cap n was less than 0, it was a shift left. Here we have cap n equaling 5. That's greater than 0, so I should be shifting right by 5. Well, let's just try it. We know that u of whatever it is that is in the argument, right, is either 1 or 0. It's 1 when the argument is greater than equal to 0, and it's 0 when the argument is less than 0. So these are just the definition of that unit step function. That function itself doesn't change. We might change the thing we're passing in the argument, but how we define the discrete time unit step doesn't change. And let me go ahead and just maybe throw some square brackets on here just to be, maybe just a little bit precise on that. So now we're going to be taking a look at u of n minus 5. So what do? I just put in n minus 5 for the argument, so I'm going to get 1 and 0, and it's 1 for when n, right, n minus 5 is greater than equal to 0, and it's 0, let's just do it otherwise. Well, let's clean this up a little bit. I can take that n minus 5 greater than or equal to 0, and I can add 5 to each side of that. That's going to give me a 1 for n greater than or equal to 5, and 0 otherwise. And so we do get the kind of a result that we would have expected. We see that this is something that turns on, but it waits until n equals 5 to turn on, right? It's been delayed. It's been delayed by 5, which is what we predicted based on the basic shift operation. So I'm going to go ahead and plug this guy in as well. So we're looking at u of n minus 5, right? And we're going to go ahead and start drawing that. So it's not on at 0 or at 1 or at 2 or at 3 or at 4, but it does turn on at 5 and 6, and it stays like that forever. And of course, for negative times, it was all zeros as well. Okay, so what am I going to do with these two guys? I am going to take the first one, that's u of n, right? And then I'm going to subtract off the second one. And I would like to go ahead and do this point by point, okay? So I'm going to draw another axis in here. I'm going to draw that other axis in here. And I'm going to go ahead and just write over here that this is going to be my u of n minus u of n minus 5, right? I'm looking at that difference right now. And I would like to do it point by point. So let me start at n equaling minus 3, that first one that I've shown on these graphs. All values n less than 0 are going to be the same to this, but I'm going to just do it for starting at minus 3. So u of n at n equals minus 3 is 0. U of n minus 5 at n equals minus 3 is also equal to 0. So I'm going to get 0 minus 0 is just going to be 0. And I can keep doing this point by point. Next one over is 0 minus 0, no problem. Next one over, 0 minus 0, no problem. Next one over is 1 minus 0, that is 1. Next one over, 1 minus 0, no problem. Next one over, 1 minus 0, no problem. 1 minus 0, no problem. 1 minus 0, no problem. That's at n equals 4. Then at 5, I get 1 minus 1, right? Because u of n minus 5 turned on at 5. That becomes 0, and everything afterwards becomes 0. So I end up getting something that turns on at 0, but turns off at 4. Many people, when they're first drawing out these discrete time signals, want to make it go out to 5, right? And they're forgetting that with discrete time signals, individual points matter. And so when that u of n minus 5 kicks on, right, that point at n equaling 5 matters, and that difference ends up giving us 0. So this thing doesn't hang out till 5, it hangs out till 4. Maybe one shorter than you would have expected. Okay, so now if I want to go ahead and take this and continue on and get the final one, right, we said that our x of n, right, was just equal to n times u of n minus u of n minus 5. Well, u of n minus u of n minus 5 is 0 everywhere except for the interval 0 to 4. And that interval 0 to 4, the value n, are 0, 1, 2, 3, and 4. So we're going to take those values, 0, 1, 2, 3, 4, and we're going to multiply them by that other thing, right? U of n minus 5, which is just a value of 1 for those range. So I'm going to get 1 times, well, 0, 1, 2, 3, or 4, and that's just going to give us 0, 1, 2, 3, and 4. So I should be able to plot that guy out as well. I'm going to go ahead and draw my axis in here and see if we can get this guy as well. So go ahead and give myself some space in here. I'm going to come out here 1, 2, 3, 4. Give myself a few extras, 5, 6, maybe minus 1, minus 2. So minus 2. Here we had 6, 5, 4, something like that, and we knew where the 0 was. And then I had what? We have like 1, 2, 3, 4. We're going to go ahead and label that one out, and I'm going to call this whole thing x of n as a function of n, and try to get into the habit of labeling all your graphs so that everything is nice and neat and readable. So at minus 2 it was 0, right? At minus 1 it was 0. At 0 it is 0. At 1 it is 1, right? At 2 it is 2. At 3 it is 3. At 4 It is 4, and then the kicker that many people get wrong, 5 is actually 0, 6 is 0, and so forth going on. So this is a 4-duration discrete time signal that is a ramp function, right? And you'll notice something else on this one. The first non-zero value, right, is at n equaling 1. If you go back to the continuous time run, we start getting non-zero values immediately after 0, right? That thing seems to start at 0. Down here in discrete time, it's a little harder. Our brains might sit there and say, yeah, the trend of that ramp kind of goes back and intercepts that point 0, but the first non-zero one is really at 1, right? And the ending point of this guy is at 4. So we have a 4-duration signal. This is the one that we're going to play with. We're going to do some various operations on it and see that we can understand reflection and shifting and doing upsampling and downsampling and maybe even some combined operations, stuff like that. So I'm going to give an alternate definition at this point because now that I've got a graph, I can think of this x, right, as being equal to what? I can think of it as being n when 1 is less than equal to n is less than or equal to 4, and it's 0 otherwise. That is a completely completely equivalent way of describing this signal. It's a little bit maybe more explicit as exactly what is being defined and when. So for the interval of integers 1 to 4, I just let it reflect that integer n, right, and it's 0 otherwise. I would also say that we could decide to describe this signal not graphically, right? We could describe it with something like a matrix or a vector notation. We'll do a little bit of that later just to show how that might be more convenient and a little bit easier than these pictures. For right now, we'll keep it with a picture. All right, so let's look at a variety of signals, and they're going to be involving these operations on the independent variable. So the first one I'm going to do is I'm going to call it y1. I'm going to let y1 of n be equal to x of minus n, right? What was this thing supposed to be? This was supposed to be reflection. Now, I can get this, right, from the definition. Y1 of n, we said, was equal to x of minus n. But what is x? X is, right, whatever the argument is, right, it's going to be giving us whatever that argument is, minus n, for 1 less than equal to, now minus n, right, and going to be less than or equal to 4, something along those lines, and it's 0 otherwise. So I just plug this into our definition that we had derived from our previous work on getting x of n. So what does that tell me? That tells me y1 of n, if I was just going to be explicit in how I do that, it's going to be equal to some stuff. I can look at the inequality first. So I have minus n between 1 and 4. If I divide both sides by minus 1, I know I flip the direction of the inequality, so I would get minus 4, right, less than or equal to n, less than or equal to n, less than or equal to minus 1. And otherwise, we still know it's going to be 0. And in that range, it's going to be minus n. All right, so let's go ahead and use that and see if we can get a plot out of y1. So I'm going to go ahead and put in my n. I'm plotting y1 of n. And I'm going to have something like minus 1, minus 2, minus 3, minus 4. Go ahead and label that in. Minus 5, maybe 1, 2, something along those lines. So I've got my axis labels in there. And I'm going to go ahead and do 1, 2, 3, 4, something like that. So we're going to go ahead and have this guy go up to a value potentially of 4, something along those lines. If I want to go ahead and plot this guy, I can just start doing it point by point. So I know it's 0 everywhere except on the interval minus 4 to minus 1. So it's 0 and 1 and 2 and minus 5. All of those guys are 0, right? Now on the interval minus 4 to minus 1, I'm just going to take the value of n, right, and I'm going to negate it. So at minus 4, take the negative of that, that's 4. So I'm going to come up here and put in my value 4. Go to minus 3, take in the negative of that, I'm going to get minus 3. Put in 2, I'm going to get minus 2. Put in 1, I'm going to get, or minus 1, I'm going to get 1. And what do I get? Well, I just get a reflection, right? I just get a reflection of that little ramp function. It got reflected about, right, that vertical axis. So reflection looks exactly like what we saw for continuous time, no problem. We can show it through the math. We could also do it graphically. It's exactly operating the way we would expect. Really no difference whatsoever. All right, so let's look at another one. Let's go ahead and look at a case of y2 of n now. So we're going to come up with a second example. And I'm going to go ahead and let this be my x of, and let's do n plus 2, something along those lines. This seems to be one of those shift operations. it shows n plus 2. If I converted that just a little bit so that I could put it in terms of the form that the book gives, it says n minus a minus 2. So you could think of that minus 2 now being my cap n. Because cap n is negative, we should be shifting left, right? So cap n less than 0, so shift left, right? So you could try to remember what was the special or particular form, x of n minus something, right? And then if that something was negative, then you shift left, and if it was positive, you do. Okay, so you could remember all these rules or whatever, or we could just go back to the definition of these functions, and we probably don't have to memorize any of these things. So let's do like we did above for the reflection, right? Let's just go look at y2 of n, right? And I know that that is x of n plus 2. But what is x? X is whatever the argument is, so that's going to be n plus 2, for 1 less than or, whoops, cancel, so we're going to go 1 less than or equal to, in this particular case, n plus 2 less than or equal to 4, 0 otherwise. I'm going to go ahead and clean this up. Y2 of n then is equal to what? Well, it's still going to be n plus 2, not much I can do on that. But for the inequality, I'm just going to subtract 2 from everywhere. So 1 minus 2 is minus 1, right? N plus 2 minus 2, that's just going to be n, right? And then I'm going to have 4 minus 2 is 2. So on the interval minus 1 to 2, I'm going to get a particular expression, and it's 0 otherwise. So let's go ahead and plot that out using the definition. Again, we just did a direct substitution in there, right? So I'm going to go ahead and put in my axis in here, and I'm going to go ahead and put in something like a minus 1, minus 2, maybe minus 3, something like that. 1, 2, 3, something like that. This is all a function of n. I'm looking at my y2 of n, and I might do something like 1, 2, 3, 4, something like that. So in this particular case, what do I know? I know anything outside the interval minus 1 to 2 is going to be 0. So at minus 3 and minus 2, right, all of those guys are 0. 3 and forward, it's all going to be 0. Only on the interval minus 1 to 2 is it non-zero. At minus 1, right, what's the value of y2 in there? I'm just going to put in my n plus 2. What is n? N is minus 1. So minus 1 plus 2 is just 1. So at my value minus 1, I'm going to get a value of 1 out. Go ahead and go to 0. Put 0 in there. 0 plus 2 is 2. So I'm going to get 2 at 0. Go ahead and look at 1. Put in 1. I'm going to get 1 plus 2. That is going to be 3, right? Just using my definition over there. And then go to the last point there. So when n is 2, I'm going to get 2 plus 2 is going to be 4, something like that. And I get again exactly what I would have expected from a shift operation. I had a little ramp function that was ramping bigger as you went to the right, right? And then I shifted this guy, and I shifted it left as we expected. I shifted it left by 2, and it certainly did that in this particular case. So again, we're not getting any surprises. All of these operations to this point have been identical in flavor and the way you would expect them to operate as you would have seen in continuous time. You would not, however, be able to do something like this. You could not say something like y3 of n, right, as being equal to x of n plus 1.5. That, right, doesn't make any kind of sense. That kind of an operation where we're doing something that's not an integer just isn't allowed. That would be a non-starter for us. So there are some differences, right? But at least to this point, as long as we're adhering to that integer value, everything seems to be the same. Let's go ahead and go to a y3 now. So I'm going to go ahead y3 of n. I would like to look at one of these cases that involves a downsample operation. And so I can let y3 of n be equal to x of 2n. Okay, so this is downsampling. This is a downsample operation. And if you remember the downsample operation, it says we are going to go ahead and discard, right? We are going to discard cap n minus 1 of cap n points, right? And just keep repeating that every single time. Let's go back and draw my x of n and think about it in terms of that. In fact, I should be able to go over here and grab this guy. So I'm going to go ahead and make a copy of this, save myself a little time. I've got this copy of x of n, and I'm going to come down here and I'm going to go ahead and place it down here as well. So I've got my copy of x of n, right? And what does the downsample operation say we should do? It says discard n minus 1. Now in this particular case, we have n equals 2, so we are going to discard, right? 1 of every 2 points, okay? And you always leave 0 alone. So we're going to leave 0, discard. Leave the next one, discard, right? So out of 2 points, discard 1. Out of 2 points, discard 1. Out of the next 2, discard. Save, discard, right? Discard, save, discard, something like that. What is the net effect of this? When I go ahead and I draw this out, if I go ahead and give myself another axis and I start thinking about what this thing looks like, right? I can go out here 1, 2, 3, 4, minus 1, minus 2. So let's go minus 2, 4, something like that. N. This is my Y3 of N. We're on our third case, right? And we are doing that downsample, which is something similar to compression. And we did a downsample here by a factor of 2. If it had been continuous time, everything would have become half as wide as it was before. Well, take a look at this guy. Its rightmost point was at 4, right? If we cut that down by a factor of 2, the rightmost one should be 2. And of course, that's exactly what happens. The 0 point right stays. That's still 0. That's no problem. But I got rid of the next one, and that means that next point comes over, right? That next point comes over, something like that. And so if I looked at all the values in here, the next point over is going to be a value of 2 now located at n equals 1. And the next one, because I skipped the 3 point, is going to come in a little bit more. So that guy is going to come up here to 4, and then the rest are going to all be zeros just because of the way this signal was. So this particular one kind of looks like a ramp that's it's ramping up faster, it appears to be, right? Because it's ramping up to its final value, not over 4 samples, right, but over 2 samples. So it does seem to operate kind of like the continuous time, right? We are squeezing this thing, we are compressing by the factor kept n equaling 2. But in order to do that, we have to throw away samples, right? We throw them away because discrete time signals are relegated. They are forced to operate just on an integer set. And so there's nowhere that I can put those pieces that would compress, if you will, to non-integer values. This value, right, if I like to look at this value at 1 and at 3 and at 5, right, if you divide that by 2, that would go to a half and 3 halves and 5 halves. Those aren't integer values. There's no place for those ones to live, so they get killed, they get destroyed, they get discarded. All the ones that I've shown in yellow or the ones with the red X's, all of these guys, right, all of those guys, all of those are lost. Those guys are lost to the abyss, never to be found again. They will never ever be recovered again. So this downsampling operation, unlike continuous time compression, is a little dangerous, right? It is a lossy operation that throws away data. And once you throw something away, it's really hard to get it back. But basic result here does look like a form of compression for discrete time. So in this next case, what I'm going to call Y4 of n, we're going to go ahead and look at this case of upsampling, so stretching a discrete time signal out. This upsampling operation, because you're trying to stretch something bigger than it originally was, we didn't have points defined to help us make that stretch, so we just insert zeros. Let's go ahead and take a look at x of n by 3. So we'd like to stretch this by a factor 3, make it 3 times larger. If you remember the rule that we talked about on this one, in this particular case then, if we are looking at this guy, we are going to insert, right, we are going to insert n minus 1 zeros between every point. In this particular case, we have n equals 3, right? So we are going to insert 2 zeros in all cases between all points. Let's go ahead and go back and grab my original x of n, and we'll think about what that thing might look like. So I'm going to go ahead and grab this guy very quickly if I can get it to do it. So got something like this, and we'll copy it over. This was our original x function, and I'm going to go ahead and paste her in there. And so there's our original x. What do I need to do in this particular case to carry out this upsample by 3? I need to put in 2 zeros, right? I need to put in 2 zeros, and I need to keep doing that. So every single interval that I have in there, I need to stuff in 2 zeros. Okay, so how would that end up looking? It would be something that if I go ahead and draw my axis again, I'm going to make it a little bit bigger this time. So I'm going to have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's go ahead and label that in there. And then I'm going to have -1, -2, -3, -4, something like that. And this is going to be my y4 of n. If I go ahead and just draw, and I'm going to do this in green just to keep the original points as originals. There's my original point, something like that. I need to insert 2 zeros. So I'm going to skip 2 over, and then I'm going to put in the next value. That was a value 1. Skip 2 over, go to the next value. That was a 2. Skip 2 over, insert the next value. That was a 3. Skip 2 over, the next value. I didn't even quite have enough. That was going to be 4, something along those lines. So I should have something that gets stretched out by a factor of 3. Take the rightmost edge of xn. It was at 4, right? Multiply that by 3. That's going to be getting stretched out, right? So we should be able to get a stretch out on that. And we will see that happen in this particular case as well. So let's go ahead and put in our red values, right? So 0 was left alone, and then I put in 2 zeros. Next one came in, that was a 1, put in 2 zeros. Next one came in a 1, put in 2 zeros. Next one came in as a 1, put in 2 zeros. Next one came in a 1, and then put in 2 zeros. Let's go ahead and just verify that all of our counting here is right. So we had that at 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and I was off on that. That's good because I was trying to figure out why that wasn't lining up where I wanted. 10, 11, 12. 12 is equal to 3 times 4, right? Stretch that rightmost edge 4 by a factor of 3, and it's now at 12, okay? In order to do that stretch, right, we had to figure out what to put in these gaps. We have these gaps sitting in here. Once we had stretched that out by a factor of 3, we needed to figure out what to put in the gaps because our original function, right, we don't see anything. There is no data defined in those gaps. There is nothing in x of n that defines what goes on in non-integer values. So the upsample rule just says we're going to guess zeros. We're going to throw in zeros. Those zeros might or might not be a good guess. At the very least, it does not destroy any data, right? It doesn't remove data like the downsampling operation does. And it does stretch things out like we would expect with this kind of an operation. It's very much similar to the expansion operation we saw in continuous time. Okay, so hopefully this gives us a basic understanding of these different operations on the independent variable. Just a real quick recap summary of some primary differences we see with discrete time. In discrete time, right? So some noteworthy differences we might put. Some noteworthy differences, right? With discrete time signals. The first one I would say in there, individual points matter. Individual points matter. We've got to be really, really careful about the inclusion, exclusion of individual points because they absolutely will matter. I think our past example demonstrated that. When we were trying to do that u of n minus u of n minus 5, it didn't seem to go out to 5 like it would have in the continuous time case. It seemed to come in one short, and that really comes down to this idea that individual points matter. The second one we might notice on there is that a downsample, right? This downsample is something where we lose data, right? We are going to lose data on the downsample operation. It's akin to the compression operation in continuous time. Operates much the same, right? Downsample by 2 does compress it by a factor 2, but in that compressing by a factor 2, we lose half of our data. If we compress by 3, we're going to lose 2/3 of our data, and so forth. 3, we might say that the upsample, right? The upsample, right? It doesn't lose data, but we insert, and you might think of this as making up, right? Data. And the ones that we do here is we put in zeros. They're a pretty safe bet. They're probably a more neutral value when we don't know any better than just about anything else. And if you take some later classes like the DSP class, you'll see that there's actually some theoretical reasons why zeros are good to put in there and how we can turn those zeros into more sensible values for some types of signals. That's for a different class. Okay, I think we've hit the basics of what we need for defining what a discrete time signal is, reminding ourselves of a basic classification, energy and power. We looked at operations on the independent variable with a focus on those differences from what we saw in continuous time. Looked at a couple signal models, the Kronecker delta function, nicer than the Dirac delta because it's completely realizable, and the unit step. Um, let's try this as just a single final example before we talk system properties. So let's try this. Let's do this idea of y of 5n as being equal to u of n. Um, let's do it like this. Let's do let's do n by 2, something like that. What should this waveform look like? This waveform, the divide by 2 should be an expansion by 2, right? It's an expansion by 2. If it was continuous time, if I did u of t by 2, it would look just like a u of t. You wouldn't be able to tell the difference. Stretching the unit step function in continuous time, because it starts at 0 and holds the same value all the way out to infinity, that's stretched by 2. You would never be able to tell the difference. So if I looked at a u of t, it looks like, this in continuous time. And if I looked at a u of t by 2, that also looks like this in continuous time. You just wouldn't have noticed a difference. Here we're doing a upsample, right, by 2. So we're going to insert 2 minus 1, or 1 0 between each sample. If I plot that guy out, take a look at what that thing looks like, right? We can think of the original values. There was a 1, there was a 1, there was a 1, there was a 1, and so forth. But then we know that we are inserting those values in between, right? We are inserting those values in between. And this is sort of different, right? This does not look exactly like a unit step. It looks like something that goes 1 0 1 0 1 0 1 0, right? It's not this nice hold constant value. So there are some differences going on here, and we do have to be careful. I also think that it's really easy using some of these notations like this u of n minus or divide by 2, and to think it means more than it does, forgetting that u of n is defined only on the integers. Some of the notations there don't make that original assumption that they're defined only on integers really obvious. And so we've got to be really careful in order to get these operations to turn out in the appropriate way. U of n divided by 2, right? U of n by 2, an upsample by 2 is not just a flat unit step, right? This is something that's going to go 1 0 1 0 1 0. So we do have to be careful. These discrete operations, discrete time operations on discrete time independent variable, the n variable, are similar, but with some distinct differences from continuous time. Okay, to end out the lecture then, let's just make a very brief comment about system properties. These are properties in the generic sense, like we talked about back in chapter 1. There's a whole bunch of system properties that we discussed. We considered almost all of these properties using continuous time system examples. So we talked about things like linearity, right? We talked about things like linearity. We talked about time invariance, right? We talked about time invariance. We talked about things like causal or causality as a system property. We talked about things like invertibility. We talked about things like BIBO stable. We talked about things like memoryless. We talked about things like realness, so memoryless. We talked about things like a realness or a real system. All of these properties, I'm going to just make it really easy for us. They're all just like the continuous time cases. Okay, the discrete time cases are all just like the continuous time cases. So we don't have to waste a bunch of time in here. You can go back and watch the lecture on continuous time system properties. They're all the same. What is linearity? Well, if an x1 goes to a y1, right, and an x2 goes to a y2, then superposition holds an ax1 plus bx2 goes to an ay1 plus by2. It tells us that summing and scaling commute with the system operator. It's all the same sort of stuff. It's the same sort of difficulties. It's the same idea as we saw for continuous time. Time invariance, if you delay the input, you get a corresponding delay in the output. Time delay in system operator commute. Causality, A system cannot depend on future inputs. It can't predict the future. Invertibility, you can always get back the input using just the output. BIBO stability, right? Any bounded output or any bounded input is guaranteed to generate a bounded output. Memorylessness, right? It can only depend on the strength of the current input. Realness, if you have a real input, you can only get a real output. We've gone through all of those before. We know they're a little bit awkward to show. Every single one of those cases is exactly the same as they were for continuous time. So take a look in the book. In chapter 3, there are some examples of showing these properties as well as proving them, and you'll notice that they look exactly the same. Next time, we are going to look at a particular class of discrete time system. That's this idea of a constant coefficient linear difference equation. This is going to be a bit like what we just got through in chapter 2 for continuous time systems described by constant coefficient linear differential equations. So chapter 3 is a little weird. Chapter 3 combines some material from chapter 1 that we just ignored for discrete time signals, and then it basically replicates all of what was in chapter 2, but for the discrete time case using difference equations. This first lecture, we did most of the catch up from chapter 1 for the discrete time cases. Now everything going forward, we're going to go and do basically what we had done in chapter 2, but do it for discrete time systems, right? We're going to do it for this class of system described by constant coefficient linear difference equations. That'll be next lecture.